Hey everyone, so I'm just going to share screen. Okay. So last time we talked about supervised and unsupervised learning and different problems that we can solve using those two approaches, like regression problems, classification problems, clustering problems. And so this time we're going to delve deeper and look into different types of regression problems. So we're going to start off with the linear regression with just one variable. And so hopefully from last time, you remember what this looks like. So this is a scatter plot of engine size of a car plotted against CO2 emissions for that specific engine size. And so what we could do with the linear regression is just come up with a continuous valued function that'll help us predict values that aren't represented by data points on this scatter plot. So that's just a recap of what we did last time. And so this is an example of what a training set would look like. So over here, some notation to keep in mind is that M is the number of training examples, which in this case would be 5. And then X is the input variable or the features, which in this case, since it's a simple linear regression with just one variable, that would just be engine size. And then on the Y-axis, we have the output variable or the target variable, which in this case is CO2 emissions. So this is what we're trying to predict. And then X comma Y enclosed in brackets is just a notation to represent a single training example. And then X superscript I comma Y superscript I is just the ith training example. So if we have 1 in place of I over here, so X superscript 1 and Y superscript 1 would just be the first training example. So that would be 2.0 for X and then 196 for Y. Okay, so model representation, hopefully we're familiar with most of what we have here, except for maybe this, maybe just H. So we start off with the training set, which we looked at in the previous slide, and then we feed that training set into our learning algorithm, and then that algorithm comes up with a hypothesis function, and then we give that hypothesis function some input, and that function will produce an output, which is the predicted value. So in this case, if we give an input for engine size, and we give that to the hypothesis function, then we'll get a predicted value of Y for the CO2 emissions for that particular engine size. So what is the hypothesis function? So for a simple linear regression where we just have one feature or one variable on the x-axis, that would, hopefully this looks familiar to most of you, and this is basically just the equation of a straight line. So h theta of x is just y, and then over here we have the gradient, so mx and plus c. So that's just the equation of a straight line. And what we need to do here is we need to come up with the best possible values of theta 0, so the y-intercept, and theta 1, the x, the gradient, so that our prediction of our predicted y values are as close as possible to the actual y values. So we have an accurate model. So how do we find the best possible values of theta 1 and theta 0? So what we use for that is something called a cost function, or the mean squared error function. So what that is it's used to measure the accuracy of our hypothesis function to help us come up with the best values of theta 0 and theta 1 so that our predicted values are as close as possible to the actual values. So the actual function is what we see here on the right side. And it might look a little scary at first, but it's actually a very simple function, and I'm going to help demystify that now. So let's start off with what we just recently learned, which is what this expression over here is. So this is just the hypothesis function, and we give it a value of we give it a specific x value. So let's say we start off with a value where x equals 1. So let's say this is what our hypothesis function predicts that the CO2 emissions will be for an engine size of 1, let's say, if we want to continue with that example. And then y superscript I is just going to be the actual value at this point, so actual y value for this value of x. So that's going to be this. And so quite simply, what this expression inside the brackets is doing is that it's finding the difference between these two, so the difference between our predicted value and the actual value. So that would be this line. Let's just use a different color for that. So that would be this line here. And so we find that difference, and then we just square it with this little square we have here. And so we're just calculating, we start from the very first training example, and then we go all the way to the last one. So M is the number of total data points that we have here. So in that case, that's going to be 5. Sorry, the number of training examples that we have here. And so we calculate the difference for each one of these, and then we square that, and then we divide that by M. So we get, so just calculating the distance and squaring that will give us the squared error, and then we want the mean squared error. So we simply divide that by the total number of training samples. So this is just a bit of a recap, just to make sure that we're all following. So this is just a reminder of what the hypothesis is, what the parameters are, and what the cost function is, and our goal is to minimize the cost function so that we can get the best possible prediction. So here we're going to look at how we can use the cost function to get the best possible values of theta 1 and theta 0. So let's say that so over here we have a graph of the value of the cost function plotted against the feature that we have. So just for a simplified example to make it easier for us to understand, we'll just look at a hypothesis function with theta 1, so just the gradient, and we'll just assume that the intercept is 0 for all of these examples here. And so our goal is to minimize the cost function, and the cost function is just the same as it would normally be, except we're just looking at it in terms of theta 1 in this case. So let's say we draw a line like this over here. And so for that, if we plot the cost function, the value of the cost function against theta 1, then we'll end up with, since this line is way too steep to be a line of best fit, it's quite a bit off from our data points. So this would be here. And so we know that we want to, so this is this isn't the lowest value that we can end up with. So we want to minimize this. So then maybe our learning algorithm will try a different line, but this one isn't steep enough. So then this theta is too small. And then eventually it'll try out this. And in this case, it fits all of our data points, which that won't always be the best case scenarios. Sometimes there will be outliers. In fact, more often than not, there will be outliers. So, and then we end up with this value here. And so what we can do with this is that we plot a parabola that will, so all of these different values of the cost function will end up forming a function that looks like a parabola. And so what we want to do with that is just use that to find the smallest possible value of the cost function. So if we start off here, then maybe our learning algorithm will realize that this is too big, and so it goes to a smaller value. And then we realize this is too small, and then it'll go to a bigger value, and then eventually end up at the minima. So now going back to a more accurate representation of the linear regression of a hypothesis for a linear regression with the y-intercept as well as the gradient. So these are our parameters, that's the cost function. Our goal is still to minimize the cost function. So if we use this hypothesis function with the intercept as well as the gradient, then we end up with a 3D curve that this is called a convex function or a bowl-shaped function. And so with this, the value of our cost function is just the height of the function above the axis here. So this is just, so our goal is just going to be to minimize that. So for this example here, so similar to what we discussed with just having theta 1, just having the gradient. So over here we have theta 1 on the y-axis and theta 0 on the x-axis. And so all of these lines over here, all of these ellipses, so at any point on the ellipse, we will be, we'll have the same value of theta 1 and theta 0. So say all of these points have the same value of theta 1 and theta 0. And so let's say we draw a line that looks like this. Now that is way off from what a good representation would look like. Also, it looks like a bit of a polynomial line. I meant to draw a straight one, but let's pretend like it's a straight line. That's just way off. And so with that, we would get, so if we have something like this, we're going to get something that is like pretty far away from the minimum. So let's say here, and then we can draw a better representation maybe. So maybe we'll draw a line that looks like this. And so maybe we'll get a bit closer to the minimum with that. And then sort of, we'll just keep drawing better and better lines. Our algorithm will just keep iterating and drawing better and better lines. And then eventually, hopefully we get to the global minimum, and that's going to be somewhere over here. Okay, so now we're going to talk about the actual algorithm that's used to minimize the cost function. And this is known as the gradient descent algorithm. And the way that it works is that we start off with some value of theta 0 and theta 1, and then we keep changing those values of theta 0 and theta 1 to reduce the value of the cost function and hopefully end up at a minimum value. So that's what this graphic that we saw earlier is representing. And so this mathematical equation here sort of defines how the gradient descent algorithm works. So the way that this would work is that so J over here would be 0 and 1. And so, for example, let's consider the instance where J is 0. So we start off with theta 0, and this expression is used for, this notation is used for assignment. So this is assigning the value of theta 0, then equals theta 0 minus alpha, which is the learning rate, multiplied by the partial derivative of the cost function with respect to theta 0. So I'm going to tell you guys what this expands into in a later slide, but for now we just need to know that we start off with, let's consider theta 0, and so we get theta 0 subtract the learning rate multiplied by whatever the partial derivative of this term is, and we put that value inside a temporary variable, temp 0, and then we do the same thing for theta 1, and we store that value inside temp 1, and then we update theta 0 and theta 1. And the reason why we have these temporary variables is that if we didn't have this temporary variable and we just updated theta 0 at this point, then when we, after this step, if we moved on to calculate the value of theta 1, then by the time that we'd get to this step, we would have already updated the value of theta 0, which would alter the value that we get here for temp 1. So it's very important to simultaneously update theta 0 and theta 1. So this is what the partial derivative of the cost function turns out to be. So this involves multivariate calculus, which we're not going to get into right now, but if, for those of you who do know calculus, you're welcome to try calculating this partial derivative yourselves, and you'll find that it does expand into these expressions here. So this is for theta 0, and this is the partial derivative of the cost function with respect to theta 1. And so that's that. And so the nice thing about using the gradient descent algorithm with a simple linear regression with just one variable is that the function is going to look something like this, as we saw earlier. And so in that case, where we won't end up with a complicated situation such as this, it doesn't matter what value of theta 0 and theta 1 we start off with, we're not going to end up at different minimums because there is only one minimum in this function, and that's the global minimum. So just looking at how the gradient descent algorithm would work, we've got a pretty good intuition of that now. But so let's say we start off at a value somewhere over here, and then the algorithm is going to find the closest, depending on what the learning rate is, it's going to find the next closest value for the lowest value of theta 0 and theta 1 that will give us the lowest value of the cost function. So that might be this, and then just we'll keep moving on until we get to a minimum over here. So that's what that does. So now the multivariate linear regression, we're just going to have multiple features that we're going to use to predict a target variable. So in this case, there's some new notation to keep in mind, which is n, which is the number of features. So before with this single variable linear regression, we talked about m, which is the number of rows or the number of training samples. And then now n is the number of features. So all of this is n. And so xi is the input features of the ith training sample. So it's going to be a vector of, let's say, for the third row, so the third training sample, this entire thing is going to be, so all of these values, if we just separate them by commas, and that would make up the x superscript ith training example of with the features. So that'll make a vector of the features. And so this subscript j represents a specific feature in the ith training example. So if we go back to the third training example, and if we consider j equals 2, then that would be the value of cylinders in the third training sample. So the hypothesis function for a multivariate linear regression is pretty similar to the one for a single variable linear regression, except we just have more variables now. And it's not super important to understand this, but if anyone's curious about how we get to this expression, then the way to do that is that we introduce just kind of this filler value for the 0th feature, which equals 1. And so once we do that because we have an n+1 number of values in terms of theta. So if we make a vector with the parameters, then we get an n+1 number of values. And so to be able to do matrix multiplication on this, we need to have an n+1 number of values in the vector with the features as well. And so that's why we introduced this filler variable, just so that we can make it so these two can be multiplied and we can get a simple expression theta t into x. And the t over here just stands for the transpose of this vector or matrix. So this slide just looks at how the implementation of the algorithm with multiple variables is pretty similar to the implementation with just one variable. So when n was 1 and we just had one feature, then we just had these two expressions with theta 0 and theta 1. And now that we have n is more than 1, we'll still have theta 0, which is the same expression as that one, and we'll still have theta 1, which is the same expression as that one, because this term is just 1. So other than that, it's the same expression. And the only difference now is that we have more variables. So we've got theta 2, we'll have a theta 3, we can have an n number of thetas, and the expression will be valid for that. So that's about it for gradient descent. Now we're going to look at something called feature scaling, which is just useful for making our gradient descent model better. So why this is important is that if we look at an example where x1, it has values ranging from 0 to 2000, and x2, let's say, it has values ranging from 1 to 5. And so if we try to plot x1 against x2, so if we've got x2 here and x1 here, then we'd end up with a very skewed contour plot. And if we try to implement a gradient descent algorithm with this, it would actually be much worse than what my drawing looks like, but that's the best that I could draw. And so with that, if we try to implement gradient descent and we sort of start off here, it's just going to be a bit of a mess, and it's just going to end up meandering around until it gets to the middle, and it's not going to be a very good implementation. And so what we could do to fix that is to divide all of the features by the max value. So in terms of x1, we just do x1 equals the actual existing value of x1 divided by the maximum value, so 2000 in this case. And for x2, similarly, we divide it by 5. And so what we want to end up with after doing that is we want every feature to be in a range from approximately -1 to 1. And so it doesn't need to be exactly -1 to 1. So if we have features that are in the range from -3 to 3, or 1 over 3, -1 over 3 to 1 over 3, then those values should be good. Doesn't need to be exactly -1 to 1. And so another thing that we could do, aside from what we saw over here, to make sure that they're on a similar scale, is something called mean normalization, where we simply take an existing value of a feature, subtract the mean from it. So we're assuming here that the mean for this is 1000, and then divide by the range or the standard deviation. So it's just going to be x1 equals x1 minus the mean over the range or standard deviation. So now we're just going to end with a little note on making sure that gradient descent is working properly, and just look at the learning rate over here. And so we just want to make sure that the learning rate isn't too big, because what will happen in that case is if we have this graph like that, and we've got this parabola over here, and this is the cost function, plotted against the parameter theta. then what would happen is that if we want to get to this minimum value, right? But if we choose a value for the learning rate that is too big, then maybe if we start off with a value over here, then what we would want is for this to kind of slowly move closer and closer to there, right? But if we choose a value for the learning rate that's too big, then it'll end up jumping over to a value up here, and then it'll jump over to values further and further away. And instead of converging to a value, it's going to diverge, which is not what we want. And so but then there's also a caveat with choosing a value of alpha that's too small, which is that then our algorithm can get really slow. So we want to find a bit of something of a middle value that's not going to end up causing our function to diverge, but it's also not going to take forever. So a good thing to do with that would be to plot a graph of the cost function against the number of iterations and see how long it's taking for it to converge and if it's converging. So that's about it for the slides. And now I'm just going to screen share and we're going to write some code for a linear regression with one variable. So the data set that we're using today is from IBM's object storage, and it shows how CO2 emissions of cars vary with different features like fuel consumption and engine size, and we'll have a look at it in a bit. And so you can download that by running this command, and we'll have this link down below. And then if you just click on this link, then that's going to automatically download the data set. So I, of course, already have that downloaded, so I won't be doing that. And so the next thing to do is to import libraries. So we need NumPy for our calculations, and then pandas for reading the CSV file. And we're also going to use matplotlib for plotting the many graphs that we will be using today to visualize our data. So the next thing is to pre-process. So for that, we're just going to start off by reading the data set. And you'll just need to copy the path for where the CSV file is on your computers. So I'm putting that in for mine, and then we can write df here just to view the data set. So as I briefly went over earlier, we just have a lot of different features here, and we can see, we're going to use them to see how they relate to CO2 emissions. So we've got fuel consumption, fuel type, transmission, the number of cylinders in a car, engine size, vehicle class, model, make, model year. And those of you with keen eyes may have noticed that there is a missing data point over here. And you won't find this in the data set that you downloaded from IBM's object storage. So I purposely edited the data file on my computer just so that I can demonstrate a bit of how we could clean data. So in this case, we've got a lot of 4s and 6s as number of cylinders for some of these cars. And what we can do about this is that we can fill this in by calculating the median value. So we can just import the math library, and then So df.cylinders.median is just going to use the median function inside the math library to calculate the median of the cylinders column. And then math.floor. So if we have an even number of rows, which we do in this case, so we might end up with two values in the middle. And so the median is going to be the average of those two values, and that might end up being a fractional number. And in that case, well, we know in this case that cylinders, I mean, you can have 4 cylinders or 5, but not 4.5, at least not to my knowledge. So we want a whole number for our approximation. So that's what math.floor does. It'll give us a whole number. And then with that, can't forget the brackets. And so we can just print out the variable that we made here that stores the value just to see what it is. And we have a 6. And now that we have the value, the next logical thing to do is to put that inside the data set where we have null values. So what fill NA does is that wherever we have any wherever we have any null values in the cylinders column, it will just fill that in with the median variable that we made. And we can check whether this worked by seeing the data set again. Wait, so df dot, wait, what went wrong here? That is marked down for some reason. Yeah, and we can see that the 4th value here that was originally null is now a 6. So the next thing that you've hopefully noticed is that a lot of these values are labels and not discrete values, such as model year, make, vehicle class. And so with a linear regression, we do want values that are discrete and continuous. So we can just alter our data set to get rid of those values. And also there's just an abundance of values to begin with. So some of them we have a lot of different values for fuel consumption. And so it will make sense just to keep one of them, since having too many different features can lead to your model overfitting. So I'll just keep we'll skip these two because they're just labels, and I'll get and of course search. So that is our new data with just these 4 columns. A lot simpler. And then from there, we can visualize the data. So we can use viz, and that's just CDF. And then so this will plot histograms, and then we can show those. Yep. So that looks a little congested. So we can just alter the dimensions. So we can just get so I think that's just going to take a second to render. Yep, there we go. So that looks a lot better, and we can see what our data looks like pretty clearly. Now, before we can make predictions with a linear regression, we want to see if the data that we're using, the variables that we're using, actually have a linear relationship. So we can use scatter plots to see that. So if we just if we can plot all of these different features against CO2 emissions to see what the relationship, what the linearity looks like. So we can start off with fuel consumption and CO2 emissions, I guess, and just go with CDF dot. On the x-axis, we have fuel consumption. And on the y-axis, we have CO2 emissions, which is our target variable. That's what we want to predict. That's a nice looking scatter plot. Wait, why is that not defined? Oh, so you need to put this inside quotation marks. My bad. Yep. And we can just copy paste this little snippet of code here to check the linearity with other features. So we can replace this with cylinders. And we can also alter the color here. So let's go with then we can also check the linearity with engine size. So this looks like the best scatter plot to me. I mean, we can see that all of them have a linear relationship, but there's a nice dispersal of data points in this one. So I'll go with that one. So now that we've seen the linearity between our variables, the next thing to do would be to do a train test split and then start making a model and then training our data. So I don't know why I did that. So np.random.rand will just generate random numbers between 0 and 1. And MSK is a Boolean array with the values true or false. And so with this, MSK is going to be true for values that are less than 0.8. And so since we're generating numbers that are between 0 and 1, there is an 80% chance for the numbers that we generate to be less than 0.8. And so for our train set, we can choose the values for which MSK is true, which is going to be approximately 80% of them. And then for our testing data, we'll use the tilde symbol. If I can find that on my keyboard. There it is. And so what that does is that that will pick the values for which MSK is false. So if it's more than or equal to 0.8, and that's going to do our train test split. And we can see what our train data is. And so that's approximately, so we had 1,066 rows to begin with. That is approximately 80% of that. And we can see our test data as well if we want to. And yeah, that looks about right. So the next thing to do would be, well, we can get a scatter plot and visualize our data with the, after the train test splits, we can visualize our training data. So we can do that as train dot. So that this will get the 0th column, which is engine size, and this is going to get the 4th column, which is CO2 emissions. And then we can get a scatter plot. So I put a period instead of a comma here. Okay, that just messed things up more. Oh, I see. Okay, that is my bad. Yep. So all good with that now. And so yeah, so I mean it looks pretty similar to what it looked like with the 1,066 values. And from here we can start building our actual model. Okay, so now we can start implementing the actual model. Building the model, sorry. Okay, so with that, so the first thing to do, I think let's just quickly recall the formula. So we just have, theta 0. If we put 0 in place of j, then theta 0 equals theta 0 minus the learning rate multiplied by 1 over the total number of points in our data set, or the total number of rows, multiplied by the sum of the difference between the predicted value minus the original value. So that's the formula. And so the first thing to do with that would be that, just for ease of writing this down, we're going to replace theta 0, which is the gradient, which is the y-intercept, with c, and then theta 1, which is the gradient, with m. So that's notation that we're familiar with. So m equals 0, and we're just going to pick the starting values that we just randomly pick a point to start off with, right? So we'll just pick 0 and 0. And for our learning rate, I'm just going to use 0.0001 because I know that this is a nice standard learning rate. And so for the number of iterations, now this depends on your learning rate. I happen to know that 1,000 is good for this implementation, but as we discussed previously in the theoretical part of this, that if we choose a smaller number of A, then that would result in greater accuracy, but also we would need more iterations because it would take more time for the for convergence to take place if we have a smaller learning rate. And so in the formula, we use m for the number of rows, but because we're using m for gradient here, since we're familiar with the use of m and c for gradient y-intercept from the y equals mx plus c line, we'll just use n, which is also easy, familiar notation for the number of something, to note the number of rows in this case, or the number of data points that we have. So those are all of our variables. And so now at this point, it's simply just using, I have these formulas taken out. So this is simply just using the simultaneous update method that we talked about earlier, where we just store the values in temporary variables and then update theta 0 and theta 1, and we consistently do this for the number of iterations that we decide upon. So that's all we're going to do here. So for I in range, so we have iterations here. And so we know that our linear regression is going to be, since it's a linear equation between two variables, it's going to be, so our y-predict is going to be a straight line. So that's literally just m into x plus c. And then just implementing the gradient descent with simultaneous updates. So we've got the temp value for theta 0, which is m in this case, and then the temp value for, sorry, m is theta 1, and then the temp value for theta 0 is temp c, and that is simply going to be, so that's going to be the current values subtracted from so this is just going to be 2 over the total number of data points that we have, multiplied by the learning rate, multiplied by the sum of the difference between our y prediction. Is that, yeah, sum of the difference between our y prediction and our actual y value, And for the partial derivative of m over here, we'll also multiply this by the x value. And we're good with that. And so we basically just do the same thing here, except we don't get this x over here. And let me just have a read through of that. Yep, that looks good. And so now we just simultaneously update m and c. So that'll just be and that's literally it. So I hope that was easy enough to follow, given that we fairly extensively went over the maths behind this. And so I'm comma C, and we can just print out the values and see what they look like. Okay, I might need to, I need to put an asterisk there. Yep, that looks good. And now that we have our model, we can use it to make predictions. So with this, to make our line, we'll just use this. So this will just give us the scatter plot. And then this one here will give us we'll plot the actual, our regression model. And then we can just label the axes. And we have had to be in here. Had to be a comma here. Yep, that should be good. And there, beautiful. So that is our regression model right there.